We're going to talk about relationships involving heats of reaction, or enthalpies of reaction. So delta H for the reaction is the amount of heat released at constant pressure or absorbed for a given chemical reaction, and it's specified per molar amounts in the given chemical equation. So as written here, 1 mole of carbon plus 1 mole of oxygen makes 1 mole of carbon dioxide, and when those amounts react, 393.5 kilojoules of energy is released. If we use twice as much stuff, it should make sense that we'll get twice as much energy, right? So if we multiply the coefficients in a reaction by a factor, here we've multiplied all of them by 2, then we multiply delta H by the same factor. You double the amounts, you get double the energy. You triple the amount, you get triple the energy. Okay? If we take that reaction and run it in the other direction, so energy is conserved, the energy of the universe is constant, so I can't create or lose energy just by running a reaction forward and backwards. So if it takes this much money to go forwards, not money, energy to go forwards, then it must release that much going backwards. So this reaction released energy, and if I take the carbon dioxide and make it back into the carbon and the oxygen, that's going to require energy. It's the same amount of energy. So if we reverse a reaction, swap the products and the reactants, we change the sign on delta H. It's just going the opposite direction. You know, I sell you a box of Girl Scout cookies for $5, and then you decide you don't want them, so you hand them back to me, and then I give you the $5 back. It's the same amount of money, just going back and forth. There's no taxes here. If we can express a reaction as a series of steps, then the delta H for the overall reaction is the sum of the heats of reaction for each step. And this works because delta H is a state function. It only depends on where you're starting and where you're ending up. It doesn't matter how you got there. This is known as Hess's law. So here we have A plus 2B, and the overall reaction is that A plus 2B goes to 2D. But we can write that as two steps. We can say that A plus 2B reacts to make C, and then the C reacts to form 2D. Hopefully you remember that you can add mathematical equations together. We can do the same thing with chemical equations. So if we were to add these together, we've got A plus 2B plus C makes C plus 2D. Here we're using up C and we're creating C just like when we did net ionic equations. We can just cross that out because it's being used and made, and so it doesn't end up in the overall reaction. So that cancels out. So we can express this overall reaction as these two individual steps. So it's a little bit like that mountain example where we're interested in the elevation change from the beginning to the end, you know, from going to the bottom. Let's call this initial and call this the final elevation. But if we took a helicopter instead of climbing up the mountain, bless you, we could say, well, I went up in the sky on the helicopter, and then I came back down. It's very sloppy, sorry. So if this is step 1 and this is step 2, the change in elevation for 1 is positive, the change in elevation for 2 is negative, but if I add those two steps together, it's the same as this. Does that make sense? Bless you. I could look at, taking a couple days to get up here and having like 2 or 3 steps up the mountain. I could go much, much higher. I could go to the moon and back if I wanted to. The change in elevation, though, is the same because it's a state function. It doesn't depend on how I got there. The change in energy for this chemical reaction is also a state function. It doesn't matter how you got from the reactants to the products. It just matters where you started and where you ended up. So we can take our reactants and go to a product that doesn't even show up in the reaction, but that reacts to form the product that we do want. And so we can say that the overall change from our reactants to our products is equal to the sum of this change and that change, just like with the elevation. Does that make sense? Now, why would we want to do this? Well, sometimes we can find a combination of reactions where we have a known delta H because someone else has measured it and put it in a book or put it on the internet or put it in a journal. And if we can find a series of reactions that we can add together to get the one we want, where we already know delta H, then we don't have to do the experiment. And that's why we would want to do this. It actually ends up making things simpler. So let's do an example. Find the heat of reaction for this reaction. We got N2O plus NO2 going to 3 NOs, just lots of N's and O's in there. The information that we have is these 3 reactions. Delta H is known for these. So what we need to do is figure out how can we combine these chemical reactions so that they add up to this one. And things that we can do are we can multiply the coefficients by a number. We can write the reaction in the reverse direction. And we can add them together. So, conceptually, this is mysterious to a lot of students. And I can't give you do this, do this, do this, you'll get the answer instructions for this. The approach I take, and these problems are much easier on an exam or homework because we typically only give you the equations you're going to need. If you're doing this in real life and you go look in the book or the back of the textbook at the chart, there's like a gazillion and 5 different reactions that you could use. And it's like, oh my goodness, how do I pick? Here, we can be pretty sure we're going to need all of these. So what I'm going to do is I'm going to look for these reactants and that product in these, and I'm going to try to just start picking my way through. So I might just start with this first reaction and say, well, does this line up with this at all? This is what I want as a product. I need NO, and NO2 is a reactant here. So I'm going to write this equation reversed. I'm going to switch the reactants and the products. So I'm going to write 2 NO2 gas. And I'm going to try to line these up so their arrows are all in the same place. It makes it a little easier. And that'll make 2 NO gas plus O2 gas. And then I'm going to keep track of what I've done to delta H. What do I need to do to this delta H when I reverse the reactants and products? I need to change the sign, right? So this is going to be plus 113.1 kilojoules. Now you wouldn't have to write the plus there, but I like to put it there just to emphasize that, yeah, I didn't just forget to write a negative sign. This is really positive. Okay, so we are closer. Now let's look at this next equation, and we see that it has NO as a product, and I need NO as a product. It's got N2 and O2 as reactants. Those aren't showing up here at all. So I'm like, well, yes?
Wait, so what is it that you're doing?
That's an excellent question. What is it that I'm doing? I am trying to find out how I can take these three chemical equations, I can reverse the reactions, I can multiply by coefficients, so that I can add these together and come up with this one.
So like in the previous slide, with like your whole A, 2B, and then 2D example, you're trying to, I guess, like add them up, almost mathematically.
It is mathematically, yes.
To where they equal the N2O.
Right. Yep. So just like you can take equations like A plus B, equals 2C, and you could say that 2C equals 5D, and then you could add those two equations, right? And you get A plus B is equal to 5D. Because if you include the 2C on both sides, what happens if I subtract 2C from both sides? They go away, yeah. So this is the same idea. You've done it with math equations. You may not remember doing it, but you did. And we can do the same thing with chemical equations. Does that help? Yeah, because knowing what the heck I'm doing here is really helpful to understanding what the heck I'm doing here. Yes? Yes, I changed the sign on delta H to positive because I reversed the reaction. I ran it backwards. So it's like doing a monetary transaction backwards, right? Instead of going to Target and buying the blanket, you've decided that you don't want it, and you go and you return it. And so instead of paying money, they give you money, okay? So it's just going in the opposite direction. Same amount of energy. Excellent questions. Well, we could work on the second equation, or we could go to the third equation. It just, whatever makes more sense to you. I'm just going to go 1, 2, 3. So I'm going to take this N2O plus O2 to 2NO. I'm going to leave this alone because this is one of my products. I'm not going to worry about the numbers of them yet. I'll worry about that in a couple minutes. So I'm just going to write this one down. Again, I want to line up the arrows. We'll make things easier later. So I've got nitrogen gas plus oxygen gas making 2 nitrogen monoxide gas. I haven't changed that equation at all, so I'm not going to change the delta H. I'm just going to copy it down. O2 does not show up in our overall reaction, right? What we've got here is we're making an O2 and then we're using up an O2, so those would cancel out. But this is going to get a little bit messy, so I don't want to do that just yet. Let's get that third equation in there. The third equation has N2O as a reactant, and that is a reactant in our ultimate equation. So I'm going to write that one down as is also. So 2N2O gas makes 2N2 gas plus O2 gas. And I'll just copy down delta H because, again, I didn't change it. 163.2. So I at least have things on the correct side of the arrow. But now I need to figure out how I can get rid of some of these things. We can do this with fractions or without fractions. Yeah.
So when you say you're trying to get everything on the same side, what do you mean by that? Because I see in the first one you moved the oxygen gas to the right side of the arrow, and then change the sign because you did that.
Right.
What was the purpose to moving over the oxygen gas? Like, what do you mean by get it?
Well, so I'm lining up the arrows here so that I can clearly see, okay, these things are all reactants, these are all products. When I look at my overall reaction, I need NO to be a product. So I don't want NO to be on the reactant side here because that's not what I've got here. I want NO2 and N2O to be on the reactant side. What's kind of confusing is I've got some other stuff in here. I've got the N2 and the O2 that don't show up in the overall reaction. So I'm kind of just leaving them alone. They're just going wherever they go. And I'm making sure this is one of my reactants, and that's one of my reactants, and this is a product. And so I've got those on the correct side of the arrow for my overall reaction. Does that help? So let's do this. I'm just going to highlight these guys. Those are the reactants and products that I need in my overall reaction. I've got these O2s and N2s that I need to get rid of. Right now I've got 1 mole of N2 on the reactant side and 2 moles on the product side. I have 1 mole of O2 on the reactant side and a total of 2 moles of O2 on the product side. It's not an equal number on each side. I can fix that in 2 ways. I can divide other things in half, or I can multiply by 2. I'm going to go with multiplying by 2. We're going to have to divide by 2 later, but conceptually I think it's a little easier. So here I have 2 N2 molecules, or 2 moles of N2. Over here I only have 1. So if I multiply that second equation by 2, if I put a 2 here and a 2 there, then this becomes a 4. And then I have to multiply delta H by 2. Now I have 2 N2 on the left side as a reactant and 2 N2 on the product side. So those cancel out. So this and this go away. Because when I have the same thing on the reactants and the products, that means that it wasn't in the overall reaction. I have 2 O2 here, and I have an O2 from the first reaction and an O2 from the second reaction. That's a total of 2. So, use a different color. This will cancel out those 2. Everybody okay with that? So then let's look at what's left. So I'm going to take what's left and I'm going to add it together. So on the reactant side, I've got 2 N2O and 2 NO2. I'm going to write this one first, just because that's how it shows up there and it's easier to look at. I've got 2 N2O gas plus 2 NO2 gas. And there's just so many N's and O's and 2's in this. On the product side, I have 2 NO and I have 4 NO. So what's 2 plus 4? 6, right? So 6 NO. And delta H for that is the sum of those guys. So I've got 113.1 plus 182.6 times 2. And then I've got a negative, I'm going to subtract 163.2. And I get 315.1 kilojoules. And this amount is correct for this chemical equation. But is this equation the same as this one? Not quite, right? This is doubled, right? This had one N2O and one NO2 and three NOs. Here, all the coefficients have been doubled. So to make it into this, I need to divide it by 2. So I'm going to divide all of these by 2. And if I divide the coefficients by 2, then I also divide delta H by 2. Because if I burn half as much wood, I get half as much heat, right? So 2 over 2 is 1, 2 over 2 is 1, 6 over 2 is 3. So that gives me the correct coefficients up here. And so delta H for this reaction, as written, is 315.1 divided by 2, 157.55 kilojoules. If we're going to keep track of sig figs, we'd round that to 157.6 kilojoules. Any questions? There will be at least one problem like this on the exam, the next exam.